Dear students, in continuation to the last class, I am going to talk about the data converters. In the last class, I have given the introduction and the overview of the data converters. In this particular video, I am going to discuss about the one particular data converter. So, as I said in the previous class, data converters are the integrated circuits. In short, we can call them as ICs. They can convert one form of data into another form. By converting the one form of data into another form, we have been getting some advantages and we have been getting some flexibility, so that we have been converting one form of data into another form. In this fourth unit, we are going to talk about the two types of data converters, which includes the analog to digital converter and the digital to analog converter. So here, if you take any digital system, it can take the signal in the form of analog and it will be converted into digital form. Then only that data will be processed, and it delivers the primary results in the digital form, and after that will be converted into analog form. Then only the programmer can see that particular analog signals. Then only the user can understand that analog results. So because we have given the input signal as analog signal, we wanted to get the output is also in the analog form. But we have been using the digital system where it can understand only the digital signals, so that the data has to be converted into digital, then after that it has to be processed, then it has to give the primary results, then that primary results has to be converted into the analog form then. So in this digital communication, we can call it as digital communication, we are required to have the analog to digital converters and the digital to analog converters. As I said in the previous class, in the real world, most of the physical quantities such as voltage, current, temperature, pressure and the time, etc. are analog in its nature. So whatever we see the quantities in the general life, in daily life, such is in the analog form. It is very difficult to process. If you wanted to process that analog signals or analog data, and if you wanted to transmit that analog data, it is very difficult. However, it can often more convenient to process, transmit or storage the physical quantity when it is converted in the digital form. The point is very clear here. We have the two forms of data, that is analog data and the digital data. So when we process our storage or when we transmit that analog data as it is, analog signal as it is, it requires the much space and it will have some difficulties. It is very difficult to process, transmit or storage the analog form of quantity. However, it can often more convenient to process or transmit that data whenever it is in the digital form. The processing and storage and the transmission, the processing or the storage and the transmitting of digital data is very simple compared to the processing and the storing and the transmitting of analog data. So by converting the analog data into digital data, we can have the more accuracy and that can be with the reduced noise. That is, we can have the more accuracy with the less noise. When the analog form of data is converted into digital form, we can have the more accuracy and we can have the reduced noise. So when we wanted to process the analog data, that is having some difficulty, and anyway that difficulty can be overcome, that difficulty can be overcome by making use of the conversion that is analog to digital. So here we can process the digital data, we can store the digital data, and we can transmit the digital data, and very easily when that data is in the digital form. So hence, to have the more accuracy and the reduced noise, and we have to have the converters which is used to convert the one form of data into another form, that is analog to digital converter. So not only to have the accuracy and the reduced noise, and to have the ease of process, transmission and storage, the analog form of data must be converted into digital form. To have the accuracy, first one, to have the reduced noise, to have the ease of process, to have the ease of transmission, and to have the ease of storage of that particular data, we have to convert the analog form of data into the digital form. The converter which converts one form of data into the another form, we can call it as a data converter. Definition is very simple. Now, definition: data converter is a device which converts the one form of data into another form. Here we have the analog form of data, we have to convert into the digital form to process and storage and to transmit the data. Another converter, that is digital to analog converter, we can understand only analog data, so that after converting into the digital and after it got processed, then we have to convert into the analog again. So there are two types of data converters, such as analog to digital converter and the digital to analog converter. So that we have the two types of converter. There are basically two types of data converter. One is analog to digital converter, in short we can call as ADC, or we can call it is A by D converter. A by D converters, that is nothing but analog to digital converter. Coming to the next one, that is a DAC, digital to analog converter. We can call it is a D by A converter. So these are the definitions and the necessity of this particular data converters. In microprocessor technology, the data can be processed in the digital form, so we have to convert the signal from analog to digital. So whatever we have been using the digital systems like microprocessor, microcontroller, encoder, decoder, all these are the digital system to process the data. All these requires the data in the form of digital only. And to have the analog form of data, the output of the digital system must be again converted into analog form. If you take any digital system, if you take the digital computer as a example, then it accept the data in the form of analog, and that analog form of data will be converted into binary bits such as zeros and ones, and then that will be processed by making use of the processor, and such that it will give the results in the again digital form only. But we cannot understand that digital form of output, so that again it has to be converted into the analog form. So the operation of any digital communication system is based on analog to digital converter and the digital to analog converter. Both the analog to digital converter and the digital to analog converters, also known as data converters, and are available in the form of integrated circuits. So now we are going through the microelectronics era, so that every device we have been getting in the form of integrated circuits, so that we have been getting these data converters also in the form of chips only, and we can call that chips are integrated circuits. The examples of circuits systems which make use of their DAC and ADC are, that is nothing but digital audio recording and the playback computers, digital calculators. All these devices can make use the analog to digital converters and the digital to analog converters. So the analog to digital converter usually makes the digital to analog converter, so that we shall start with the our discussion is with the DAC followed by the ADC. If you take the analog to digital converter. If you take analog to digital converter makes use of the digital to analog converter only. So that first we'll talk about the digital to analog converters. After that we are going to see the analog to digital converter. So now digital to analog converter definition is very simple. We know the definition of the digital to analog converter. So it is an integrated circuit. It is one form of the data converter which converts the digital form of data into the analog form. A converter which converts the data from analog, so data from digital to analog form, of the data is called, it is a digital to analog converter. It is also abbreviated as DAC, and it is also called as a D by A converter also. We know this one. A digital to analog converter accepts the n bit information, n bit data. We can call it is the digital to analog converter. Input of the digital to analog converter is a binary form of data. That is, we can have the n bit of information can be accepted as input. In n bit we can identify the MSBs and LSBs. MSB is nothing but what it is, most significant bit, and LSB is nothing but least significant bit. So in DAC it accepts n bit binary word, and such as we can represent, that is D1 to Dn. D1 we can call it is as LSB, and Dn we can call it is MSB. Otherwise you can write like this: Dn minus 1, and this is D3, D2 or D1. Now here D1 is a LSB, least significant bit. The bit which is having the least positional weight, that is called as it is a least significant bit, and this is MSB, we can call it is a most significant bit. A binary digit which is having the more positional weight, then that is called as MSB. So this word can be accepted as an input for the digital to analog converter. Then that converter is going to convert this digital form of data into its equivalent analog form. Then now we are going to talk about some basic DAC methods, basic digital to analog converters method. Basically, digital to analog conversion is a process of converting a binary into its voltage or its current. Generally what the mechanism is involved in the digital to analog converter, we will be giving the binary data to the DAC, digital to analog converter. This is a binary data or the digital signals, we can call binary data or the digital signal, that will be converted its equivalent voltage or its equivalent current. That means what, from the DAC we can get the two possible outputs. One is we can have the output voltage or we can have the output current. So the input of the DAC, digital to analog converter, that is about the binary, straight binary or BCD, and that will be converted into the output voltage or output current, which is proportional to the digital value. So for a 3 DAC, that means what, if you give the 3 bit word or 3 bit binary number, there are 2 power of 3 possible combinations of input. We know that, for example, if you wanted to give the n number of bits, in the word, so that combination of input signals will be the 2 power of n. And all these things we have studied in the starting units of the digital system. For example, we are having the two bits only, that is A and B, so that we can have the 2 power of 2 combinations, such as 0 0 0 1 1 0 and 1 1. So if number of bits are n, so that we can have the 2 power of n combinations of input signal, and that 2 power of n combinations will be applied as input, such that the corresponding output voltage and the output current can be provided as output. So that here, if the DAC is with the 3 bit binary number, it is with the 3 bit binary input, so that it can have the 2 power of 3 combinations, so that 8 combination. If it is with the n number of, so that it can have the 2 power of n combinations. Likewise, we can have the size of the digital to analog converter. Now the analog output is proportional to the input binary number. The block diagram of the digital to analog converter. This is the block diagram of digital to analog converter. This is the data. This is a binary data which we wanted to give the input of the digital to analog converter. And to on this digital to analog converter, we will be giving one reference voltage. We can call it as VR, and based on VR and the based on the VR voltage and the binary data we have been giving as an input to the digital to analog converter, corresponding output will be generated, corresponding output will be provided, that may be voltage or current. So here this one is what? It is a binary word, or we can call it as a binary data, and that is nothing but binary word or the binary data, so that as input. Now we will be getting here voltage or current as output. This is the block diagram of the any digital to analog converter block diagram. It accepts the inputs in the form of binary data, and which able to provide the output either in the voltage or in the current. And to on this device, to make the conversion, we will be applying some reference voltage, that is VR. Then I am going to explain the relation between the output voltage and all the input signals and the reference voltage. Then I am going to give the relation between all those things with this equation now. Now, see, for voltage output, that is, for example, we know that the digital to analog converter can be able to provide the two types of output. One is voltage, another one is current, and this is the output voltage equation. VO is nothing but output voltage is equals to K. K is nothing but it is a scaling factor. This is always approximately equals to 1. This is a scaling factor which is always approximately equals to 1. And VFS is nothing but it is a full scale voltage, and followed by the and a D1, whatever the bits we have applied, whatever the data we have applied as an input for the digital to analog converter. For here we have been assuming that is n number of bits are there in that particular data, that is D1, D2, D3 and up to Dn, so that it will be multiplied with the D1 into 2 to the power minus 1 and plus D2 into 2 to the power minus 2. Like that we can have the standard equation of that particular conversion. That means what? If you know all these values, if you know the K value, VF as full scale voltage, that is nothing but sometimes we can call it as a reference voltage also. And D1 that means what? It is a LSB, we can call LSB nothing but a least significant bit, and DN is nothing but most significant bit. By having all these things, we can theoretically also we can verify by making use of this equation. Here VO is nothing but it is the output voltage, K is a scaling factor, VFS is nothing but a full scale output voltage, and D1 to Dn is nothing but it is a n bit binary fractional word, and the decimal point is located in the left. And D1 is we can call it is LSB, and Dn we can call it is MSB, and LSB can be LSB is nothing but LSB we can have LSB value, we can have full scale voltage by 2 power of n, and MSB we can have that is full scale voltage by the 2 power of 1 we can have, like that. Then in for 2 marks and the 3 marks you can be asked to solve some problem, and by giving the decimal word, by giving the binary word, we are going to you people are going to ask you to solve the problem. Try to find out the MSB and try to find out the LSB. LSB is nothing but what? Least significant bit. MSB is nothing but most significant bit. Likewise, we can calculate MSB and LSB and the output voltage. Here these three equations are very important. This is the output voltage, and in corresponding with the input digital data such as D1, D2, D3, Dn. D1 is LSB and Dn is MSB, and here K is a scaling factor, and these three equations are very important. There are various ways to implement the digital to analog converter. there here we shall discuss the following resistive techniques. There are various types of digital to analog converters are there, in which we are going to discuss the resistive type only, because in the syllabus we are having only resistive type for digital to analog converters are there. That resistive type, in which we are having the three, in which the first one is weighted resistor, second one is R2 to R ladder DAC, next one is inverted R2 to R ladder DAC. And from these three topics, one question will be asked for the direct long answer question in the exam. So that if you are good at the three digital to analog converter, you can easily get the 15 marks from the third unit, that fourth unit. So that I request you all put some additional interest in understanding the fourth unit, as the fourth unit is very simple and easiest unit among all the units of the digital electronics and logic design. So that there are three digital to analog converters are there. One is weighted resistor digital to analog converter, another one is R2 to R ladder digital to analog converter, next one is inverted R2 to R digital to analog converter. Then I'm going to talk about the one particular digital to analog converter, that is weighted resistor digital to analog converter. In this class I'm going to explain the introduction of that digital to analog converter. In the next class I'm going to explain the in what way it convert the binary form of data into the digital form. So it is a weighted resistor DAC. It is one of the simplest digital to analog converter, which uses the summing amplifier with the binary weighted resistor network. It has n electronic switches D1, D2, D2 up to the Dn, controlled by the binary input word. And if the binary input to the particular switch is 1, it connects, otherwise it is going to be open, and based on the two operations and it is going to operate. One is if the switch is on, then reference voltage is connected to that particular line, and such that converter is going to convert the digital form of data into analog one. Next one is if the switch is off, then VR is not going to be applied. That means what? It is a open circuit now, and such that no voltage is carried to the DAC, such that no output will be provided. So like that, based on these two operations, we are going to have the weighted resistor digital to analog converter. Anyway, in tomorrow's class we are going to discuss in detailed weighted resistor digital to analog converter with its diagram and operation. If you explain its diagram and operation and some transfer characteristics of that particular weighted resistor DAC, you can easily claim the 15 marks. You can easily attempt the 15 marks in the external exam. So that students, please put some additional interest on the fourth unit, such that you can easily get the 15 marks from the fourth unit. In tomorrow's class I am going to continue the same weighted resistor DAC, such that everyone will be clear with the weighted resistor DAC. Thank you, students.